Hello Calc 3, welcome back to another video. So this video is scheduled for May 13th. This is going to be the first of 4 different videos that I upload for May 13th. So in this video we're going through section 12.3, at least the first half of it, and section 12.3 is on the dot product. So in the last section, the last video, we introduced 2 types of vector operations. We had vector addition as well as scalar multiplication. But in this section, we introduce another kind of vector operation, and this one is going to be called the dot product. And after we introduce this new notion of the dot product, we're going to show how the dot product can be used to find the angle between 2 vectors in the plane or in space, as well as the projection of one vector onto another vector. And if you don't know exactly what I mean by the projection of one vector onto another, don't worry about that because we're going to define it somewhere below here. All right. So we're going to start off with just the straight definition of the dot product. If we have 2 vectors, u and v, and I have them listed with their component form there, then the dot product of our vectors u and v, which we denote u dot v, hence the name dot product, is defined as follows. So we take the first component of u and multiply it with the first component of v, and then we add the second component of u times the second component of v, and then we add the third component of u times the third component of v. And we should notice right away that when we take the dot product of 2 vectors, the output is a scalar. It is just a number, it is not a vector. To see why, go up here and look at the right side of this equation here. Notice that all of the variables that appear in this equation are just real numbers that we're multiplying and adding together. And I want to go through just a few properties of the dot product. So let's let u, v, and w just be arbitrary vectors, and let c be some scalar. Then we have the following 5 properties here. I'm not going to go through all of the properties, but I thought it would be nice to just list them for you so you have access to them. They're also listed in your book. I will make mention of the first property. So the dot product is commutative. And then I give a proof of the second property below. The book offers a proof of property 1 and property 3. And I'll also make special mention of property 4 because it's something that I use in a proof down below. So if you take a vector and you take the dot product with itself, you end up with the length of the vector squared. And that's not too tough to see. So if I'll actually just write this one down. So if I take u dot product with u, I get u1 squared plus u2 squared plus u3 squared. And remember that the length of u, or the magnitude of the vector u, is going to be the square root of this. So if I square that, of course, I'm going to get back to my u1 squared plus u2 squared plus u3 squared, which we just said is equal to the dot product of u with itself. All right, so let's move down to the proof of the second property. I think I only have the first part of the second property. So we're trying to show that the scalar c times the vector u in parentheses dotted with the vector v here is equal to this expression. So the vector u dot product with c times the vector v. And this really just follows from the definition of the operations that we've already defined. So you can break up your vectors here into their component forms, and c times our vector u. To get that, we're going to distribute c through the components of u and get this expression here, c times u1, c times u2, c times u3. Those are the components of the vectors c times u. And again, we're still taking the dot product with our vector v over here. Now we follow the definition of the dot product to get from there to here. So we just multiply the components and add them together. And the crucial step for this proof, which I have given in blue here, is the commutativity of scalar multiplication. So again, C U1 V1, C U2 V2, all of these different variables are just real numbers, which means that when we multiply them, we can change their orders because multiplication is commutative. So we can switch U1 and C. When we move to this equation here, we can switch U2 and C. We can switch U3 and C. And then if we look at this new equation that we have here, this ends up being the same as our vector U in component form, the dot product of our vector U with C times V1, C times V2, C times V3, this vector over here. And of course, that is just the vector C times V. And so we end up showing that our original expression up here, this C times the vector U, the dot product with V, is equal to the vector U with the dot product with C times V. And the second part of the proof is to show that both of these expressions are equal to C times the dot product of U and V, but I am going to leave that to you. And let's just move on to a couple of examples, just applying some definitions here. So let's say we have the vector 1, 2, 3 and the vector 2, 2, 2, and we want to find the dot product between them. Again, we're going to take the first component of V, which is 1, multiply with the first component of U, which is 2. So we get a 1 times 2. We do the same thing with the second components to get a 2 times 2. And then the same thing with the third components to get a 3 times 2. And then we can add these up, and eventually we find that the dot product is going to equal 12. Again, notice here, when we take the dot product of two vectors, we should just get a number. We should not get another vector. And one other example, just changing the numbers up a bit. Let's say that V is equal to -1, 2, -3, and U is equal to -2, -2, -2. And again, we want to find the dot product. So we're going to multiply the components just as we did before. We get -1 times -2 plus 2 times -2 plus a -3 times a -2, and we end up finding that the dot product is equal to 4. The point of this second example here is just to show that the definition does not change regardless of whether the components of our vectors are positive or negative. It is possible to get a dot product that is negative. So just heads up for that. All right, so let's move on to an application of the dot product right away to another concept for vectors and space. So if we have two vectors in space and we place them so that their initial points are the same, as you can kind of see in the diagram I have drawn right below there, then we have an angle that is created between our two vectors, which is the angle that I have denoted theta in the diagram. And let's note right away that theta will always be between 0 and pi. What I mean by that is that technically, when we have our vectors in this plane here, we could say that there's an angle between the vectors that goes around this way. Let's call that like theta prime or something. But theta prime is never going to be the angle we're talking about. We're always talking about the angle between the vectors that is between 0 and pi. And also note that if U and V have the same direction, then the angle between them is going to be 0 degrees or 0 radians. And if U and V have opposite directions, but they still lie on the same line, then we're going to say that the angle between them is equal to 180 degrees or pi radians. So the next task for us to go through here is to find an equation that allows us to kind of efficiently calculate the angle between two arbitrary vectors in space. The book offers this as a proof, but I think that it's actually better to offer this line of reasoning as a way to kind of build or motivate the theorem that we get at the bottom here. So let's go through the proof, but I'm going to treat it as a motivation here. So let u and v just be arbitrary vectors in space. Then we can line them up so they have the same initial point. And we end up getting this diagram that I have drawn here. So we have our vector u, we have our vector v, and then I have theta drawn between the two vectors. And I also added this vector w in yellow. So we draw a third vector w that connects the terminal points of u and v. And notice right away that the vector w is the same as the vector u minus the vector v. So I actually made that note down here, but I'll say it right away, just so that you can keep that in mind. Okay, so clearly we have a triangle here drawn, and we can apply the law of cosines to our triangle. If you don't know, or if you don't remember what the law of cosines is, check out section 1.3 in the textbook. It should cover the law of cosines in there. But the law of cosines gives us that the length of w squared is equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times cosine of our angle theta. This is just directly applying the law of cosines, nothing too special here. And now we can rearrange the equation just by adding things to different sides to get this equation. And here's a key step. So from this equation right here down to this equation, we are applying property 4 of the dot product, which I made special mention of before. Remember that the length of u squared is going to be equal to u, the dot product of u with itself. Likewise, the length of v squared is the dot product of v with itself, and we can say the same thing about our vector w. And now we make special notice of the fact that w is equal to the vector u minus the vector v. And we do a little bit of substitution. So first we expand, let me get a different color, we expand u dot product u to get this expression here. We expand v dot product v to get this expression here. And then we write w as u1 minus v1, u2 minus v2, u3 minus v3, and again we expand the same way with w dot w to get this. And from here it's really just a bunch of algebra on the right side of this equation, so I'm not going to say much about what's going on inside of this. It's just squaring the u1 minus v1, the u2 minus v2, etc. And after we square those, a bunch of these terms cancel out. So all of the, well, let me just give one example here. So we have u1 squared, that'll cancel with the minus u1 squared over here. The v1 squared is going to cancel with the minus v1 squared over here. And the same thing happens with all of our squared terms. And we're left with only 2 times u1 v1 plus 2 times u2 v2 plus 2 times u3 v3. And of course we can factor a 2 out of that, and we're left with 2 times, maybe I'll put some parentheses around this. So 2 times the dot product of u and v. The 2's will cancel on either side of the equation here. And then we can divide by the length of u and the length of v, assuming that u and v are non-zero, of course. And we get that cosine theta is equal to the dot product of u and v divided by the length of u divided by the length of v. Now we can take the inverse cosine of both sides of the equation, and finally we end up at what we wanted to get to here. which is that theta is equal to the inverse cosine of u dot v over the length of u times the length of v. And this will lead us into probably the primary theorem of this whole section right here. So if we have two vectors, u and v, either in space or in the plane, and they are non-zero vectors, then the angle theta between our vectors u and v is given by this expression right here, or this equation here. So the inverse cosine of u dot v over the length of u over the length of v. Okay, so it's probably best to go right into an example from here. So let's say that we have the two vectors u equal to I minus 2j minus 2k, and v equal to 6i plus 3j plus 2k. And we want to find the angle between our two vectors. Then we're going to use the theorem that we just derived above. So theta is equal to the inverse cosine of u dot v divided by the magnitudes of u and v. So let's start by finding the magnitude of u. That will be the square root of 1 squared plus minus 2 squared plus minus 2 squared. And we end up getting the square root of 9, which is equal to 3. Then we can also find the magnitude of our vector v by taking the square root of 6 squared plus 3 squared plus 2 squared. And ultimately we end up finding that the magnitude of v is equal to 7. In both of these cases, we are just using the definition of magnitude of a vector that we talked about in section 12.2. Yeah, 12.2. And the last thing we need to find is the dot product of u and v. So we take the first component of u times the first component of v, second component of u times the second component of v, and the third component of u times the third component of v. And we add these products together and end up finding that the dot product is equal to minus 4 over here. And so using our equation, which is given right here, we find that theta is equal to the inverse cosine of minus 4 over 21. And if you plug that into a calculator, you find that theta is approximately 1.76 radians or 101 degrees. Yeah, so for a lot of these trig functions where it's not clear how to approximate them, feel free to just plug those into a calculator or onto some program that you find online. Either one will be fine. And now for the last part of this video, let's talk about orthogonal vectors. So we have already shown that cosine of theta is equal to the dot product of u and v divided by the magnitudes of u and v. But if we multiply by the magnitude of u and v to both sides of this equation, we find that the dot product of u and v is equal to the magnitude of u times the magnitude of v times cosine of theta, where theta is the angle between our vectors u and v. So let's do a little bit of math exploration here. If theta is equal to 90 degrees, then using the equation that I just referenced up here, this one, then u dot v is equal to the magnitude of u times the magnitude of v times the cosine of 90 degrees. But the cosine of 90 degrees is equal to 0, and this of course implies that our dot product is equal to 0. On the other hand, if the dot product of u and v is equal to 0, let's assume that this is the case, then u, or the magnitude of u times the magnitude of v times cosine of theta is equal to 0, which implies that either u is the 0 vector, v is the 0 vector, or cosine of theta is equal to 0. So if our dot product, u dot v, is equal to 0, either u or v is the 0 vector or theta is equal to 90 degrees. So if u and v are both non-zero vectors and the dot product is equal to 0, it implies that the angle between u and v has to be 90 degrees. And this leads into the definition of orthogonal vectors. So two vectors, u and v, are orthogonal if and only if u dot v is equal to 0. And again, as I just said, if u and v are both non-zero vectors, then u and v are orthogonal if and only if theta equals 90 degrees, where theta is the angle between them. So if and only if the two vectors are perpendicular. And finally, for a last example for the first half of section 12.3, let's say that we want to show the two vectors u and v, as I have listed here, are orthogonal vectors. To do that, we're going to take the dot product and show the dot product is equal to 0. So we take the dot product of u and v, and we get 1 times -1 plus 2 times 2 plus 3 times -1, which is equal to -1 plus 4 minus 3, which is equal to 0. And that proves that the vectors u and v are orthogonal. Okay, so that is the end of the material for the first half of section 12.3. Just keep a lookout for the second half of section 12.3.